Let us look at question number 20, set 2, Civil Engineering, K 2021. A prop cantilever beam XY with an internal hinge at the middle is carrying a uniformly distributed load of 10 kN per meter as shown in the figure. The vertical reaction at support X in kilonewton is asked, and we are expected to report our answer as an integer. The relevant NPTEL course cited below deals with this topic in more detail. Students are encouraged to watch this lecture. However, we will be looking at some fundamentals pertaining to equilibrium as we go on in solving this problem. Let us understand some fundamentals relating to equilibrium. Let us consider a simply supported beam with a hinged end at one end and a roller at the other, and let this be subjected to some random loading. Now, if we were to draw the free body diagram of this simply supported beam, we know that we would be having two reactions at the hinged end and one reaction at the roller. Let us call it V1, V2, and H. For further analysis of the beam, our first goal is to calculate these unknown reactions. Let this be the XY plane. Now, for any beam where we are able to calculate the unknown reaction solely based on the equilibrium equations, which in the 2D case are sigma Fx equal to 0, sigma Fy equal to 0, and sigma mg equals to 0. If we are solely able to find all the reactions by applying these three equations, then the beam is said to be statically determinate. In case the number of unknown reactions exceed the number of equilibrium equations available, then the beam is said to be statically indeterminate. In such cases, we either have to bring in the displacement picture of the beam to get the additional equations or look for some other via media. Now, if we were to consider a prop cantilever beam subjected to some random load, and if we were to draw its free body diagram, we know that a fixed end has three unknowns and a roller has one unknown reaction. Let us call this V1, V2, H, and M. Now we can clearly see that the number of unknowns exceeds the number of equilibrium equations available. Hence, a prop cantilever beam is indeterminate to the first degree. This essentially means that we need one additional equation in order to solve for all the unknowns. Now, either we can bring in the displacement of the beam into the picture and solve for this unknown, or we can introduce some feature into the beam which would allow us to solve for one additional unknown. Let us say we introduce an internal hinge. We know that a hinge doesn't support a moment. We get one additional equation of sum of the moments equaling 0 at the internal hinge, which will allow us to solve this problem. If we were to look at the construction of this prop cantilever beam, this would essentially mean that two separate beams, let us call them 1 and 2, are stitched together at this point using a hinge. Further, the principle of equilibrium states that if a system is in equilibrium, any subsystem derived from that original system also needs to satisfy the equilibrium equations. Hence, if we consider this beam to be made up of two subsystems, namely beam 1 and beam 2, both the subsystems individually have to satisfy the equilibrium equations. If we were to draw the free body diagram of these two subsystems, we know that a fixed end again has three unknowns and the roller support provides one restraint. We know that hinges cannot support moments but can transfer vertical and horizontal forces, let us say V and H, and by Newton's third law we can see that this would be equal and opposite onto the other beam. Let us call this V1, V2, H1 and M. Now, since every subsystem has to satisfy equilibrium, we have three equilibrium equations for each of the beams to solve for the unknowns. Hence, we can see that we have 6 unknowns here and we have 6 equations, and this helps us solve the problem purely using statics. This is the principle that goes behind solving the problem at hand. Let us now look at the problem at hand. We can see that this beam is made up of two subsystems, and if we were to draw the free body diagram of each of the subsystems, let us say V1, H1, M, we would see that V and H would be the shears. Now, if we look at the second beam, we can see that sigma fx equals 0 gives us h equals 0, sigma fy equals 0 plus v2 equals 10 into 2, which is 20 kilonewton, and sigma moment about the right end, if we take, we can see that 10 into 2 squared by 2 equals 0,
which gives us V equal to 10 kilonewton. Now that we have solved for H and V, we can take up the second problem by replacing this equal to 10 kilonewton and H equaling 0. And we can again apply the equilibrium equations. Sigma Fy equals 0 gives us P1 minus 10 into 2 equaling 0, or V1 equals 30 kilonewton. We can also solve for H1 and M similarly. However, in our question we are required to calculate V1 alone and report it in kilonewton. Hence, V1, which is the vertical reaction at X, equals 30 kilonewton, and this is our final answer. Thank you.